Hello and welcome to my two-part session on this Firebird conference. It was supposed to be a 1-hour session, but then I realized that I didn't have time to show any SQL examples, and I really wanted to do that. And the time slot after my presentation was still empty, so Holger said, okay, do it 2 hours. Which I kindly accepted, so thanks, Holger. Short introduction to myself. My name is Frank Ingermann. Some of you may know me because I'm around with Firebird for pretty long. Actually, I'm one of the founding members of the Firebird Foundation, which is also 10 years old now. So it's celebration time this year, 10 years of Firebird. And I even found back my first Firebird t-shirt that we made for the first conference. It's pretty worn out by now, but it still works. Apart from being busy with Firebird, I'm a senior developer for a small software company in Aachen here in Germany, which is called Klarpartner AG. And we're making software basically for quality control in production, especially for cosmetical industry and pharmaceutical industry. And so we have a lot to do with recipes and recipe databases. And that's how the idea came about to make a session about this, because I guess any one of you has, at some point in his career, dealt with recursive data structures. At least when you work with Windows Explorer, recursive data structures. But they're much more common than you would think. Even if you have something as stupid as items, and the items are organized in categories, or you could say that's a lookup. But if you have categories with subcategories, you have a tree. So it's pretty common. So, welcome to the session. Say Sparky's 1 and 2. Sparky 1 is here. Sparky 2 wasn't feeling too well. He's back at the hotel. No, actually, I just couldn't carry him anymore. So, yeah, I think Sparky 2 is outside on the desk. This is 1, and the other one I have is 3. Okay, so what is this session basically about? This session is a piece of cake. Now, that's not really true. Actually, this session is about a piece of cake. About this piece of cake. You see there. We'll get to that later on. I'm afraid only in the second hour of the presentation, but then you'll understand what I mean. Okay, just give a quick overview. First, I'll have some slides about general introduction to trees, what we have, what we call parts of trees, and things you have to be aware of when dealing with tree structures. Then the first and shortest part really is about recursive store procs, because I guess any one of you has worked with recursive data structures, has sometime been writing recursive store procs, haven't you? Whom of you has ever written a recursive store procedure? Hands up. Oh, that's quite a lot, okay. But in modern Firebird, there's some alternatives to that. And actually, the first alternative I'm going to show has nothing to do with Firebird in specific. It's just another way of dealing with trees. But I find that very interesting, so I wanted to show you. It's called nested sets. Who of you has ever heard of nested sets? Not so many. Who of you has actually worked with nested sets? Okay, so this should be kind of interesting, I hope. And the next and biggest part will be recursive common table expressions, which were introduced in Firebird 2.1, and I think is really a killer feature. This is really cool. It's amazing what you can do with those things. So that's why I guess the first hour will be the first 2 topics, and then somewhere at the end of nested sets we'll have a break, and the second hour will be mostly focusing on recursive CTEs and also in some comparison between the 3 ways of dealing with trees. And in between, I'll try and always switch to my SQL editor and show some real-world SQL examples so you can really see in practice what I'm talking about. Okay, just some definition slides. What is a tree at all? Tree has a single root, obviously. It has some forks, branches, that we call nodes in IT. And unless you're so stupid as me to take a photograph of a tree in January, it also has leaves. but our trees all have leaves. So this slide looks a bit nice, but all the pointers are a bit across each other. So, programmers are pragmatic thinking guys. This looks weird, so what we do is we just hang the tree up the ceiling, and then we get a tree like we know it. Okay, to be more IT-like, a tree looks like this. A bit boring, but anyway. So first of all the trees that we deal with usually have one single root node. Just to say this up front, all that you see there are nodes. We just have special names for the uppermost and the lowermost nodes. And the root node is defined by that it has no parent node, so there's nothing above it. Then we have the general nodes that can have 0 or 1 parent node. When it has 0, it's the root node, obviously. Any node depends on the type of tree, I'll come to that later, has 0 through n child nodes, which are below it. And then obviously we have the leaf nodes, which are the ones that have nothing below them. So it's just the lower end of the tree. And leaves and nodes can also have neighbors, or what you call siblings. I mentioned this term siblings here because it made me crazy when I started working with virtual tree view. That's control in Delphi. It's very powerful for handling trees. And they were always talking about siblings, and I have no idea what it meant. So, some more terms. When you see this tree, there's a level to each node, where we usually start counting with 0. And the entire tree has a height of 3 in that case. And here you can see what I mean with confusion with the siblings, because these two leaves are siblings. They have the same parent node. And these two aren't. They're on the same level, but they have different parent nodes, so they're not siblings. This confused me a lot when working with virtual tree views, so I just wanted to mention that. So if you imagine this was a family tree, the siblings are really brothers and sisters, and not nephews or cousins or whatever. Okay, we have basically 2 types of recursions in trees. First, and the most common one, is the top-down recursion, which means that you start at some top node. It doesn't have to be root, but it usually is root. And then you walk down the tree and traverse all the childs exactly once. It's typical tree traversal, you all know that. But there's also bottom-up recursion. This is less common, where you start with the child node and go up until you hit root. This is the typical case when you have a file system and you're in some sub directory and have a file name and you want to have the entire path. That's a bottom-up recursion. But usually this isn't done with recursion because it can be done much more efficiently with iteration. Okay, tree types. There's actually a distinction between a lot of different tree types. I just made a distinction between 2 basic types here to keep it simple. First type are binary trees. Binary trees are defined by the fact that every node can have a maximum of 2 child nodes, no more. So usually these are called left or right nodes, or black or red or whatever. And actually the concept is pretty old. There were these 2, I think Finnish guys, I'm not sure, Elzenbelsky and Landis, who wrote down a paper about that in 1962 with algorithms, how you could balance binary trees and keep them in good shape. And then, more general, we have AND or BIA trees, which means that obviously nodes can have more than 2 subnodes. So this can be 0 through n subnodes, and what we distinguish here is trees where you have a fixed number of n, so you have a maximum number of nodes per parent node. These are usually B trees. And then you have the typical unlimited n type trees, like file systems, where n isn't really so limited if you're working on Windows. Ever tried pumping 10,000 files into the same directory? I think it goes on the Windows 7, but there were Windows versions where this wasn't a good idea. But this is the typical structure of file systems. So, more generalized, binary trees are just a special case of n trees. They basically all work the same, but just the number of n is limited. Okay, one thing you have to deal with when you're dealing with trees is to keep your trees in good shape. depending on what you do, you can't always do this because sometimes just the data induces the structure of your tree, so you can't change much about it. But if you can change much about it, especially when you're dealing with search trees, then you should consider this. You can have healthy trees looking like this. So they're nicely, evenly distributed and filled. They're as flat as possible, so we don't want height, because each step in level means a new recursive call, and recursive calls are always expensive. So the fewer recursion levels you have, the faster you can traverse that tree. And this one here is 31 nodes, but it's only 4 levels deep, so that's pretty good. Actually, for a search tree, that's optimum, the best you can have. Opposite is an unhealthy tree that looks like this. Technically, it's also a tree, but it doesn't really look like a tree. And this is the first thing you hit when you try to build a binary search tree and pump in data, and the data is already sorted in the way that you want to get it out. If you don't balance the tree, it'll look like this. So that's why what we call degeneration. You can have a degenerated tree that isn't really a tree anymore. And it takes a lot of work to get to few data, because you can see the middle amount of hops you need in that upper tree is maximum 2 or 3 to get to 31 nodes. And here you need an average of 4 or 5 to get to only 8 nodes. So that's always something you have to keep in mind when you're dealing with trees, because there's no way around this. Recursion will always be slower than iteration. It's just because whatever you do, you need a call stack, you need to prepare stack frames in the programming language, allocating memory, stuff like that. So every recursion call is expensive compared to just another loop in a loop. Okay, let's have a word about relations of nodes in trees. Classical case is the owner or containing relation, which means, for instance, in a file system, that each file you have in the file system is virtually owned by the directory it's in. The directory contains the file, and the directory is the owner of the file. Which simply means, first of all, that each file can only be in one directory at a time, not in 2 at the same time. And, obviously, if you delete the directory, it will delete all the files in it, because they're contained. Now, opposed to that, you can also have referencing relations. And actually, in databases, I've come across more referencing relations than containing relations. Which means, like, for instance, in our classical recipe database, you can make a recipe containing of several sub-recipes. We'll see that on that example later on. So each recipe can be made of any amount of sub-recipes, but any of those sub-recipes can at the same time be part of other recipes, because they're only referenced and not contained. And obviously, when you delete one of your master recipes, you don't want to delete all the sub-recipes, because otherwise they would be gone in the other master recipes as well. So that's just a different kind of owning relationship. So basically, this means that a node in one tree can be a link to the root node in another tree, but still you want to traverse the whole thing. We'll see that later. Okay, one word about node types. I didn't find any better word for it, so I call it morphology, because what I want to make clear is the distinction between homogeneous and heterogeneous trees. In a homogeneous tree, all of the nodes contain the same data. So in SQL, this classically means that all the node data comes from one table that is just interlinked. But you can also have heterogeneous trees, and that's really where trees start getting interesting for me. That means that every node can have a different data type than the other nodes in the tree. So in SQL, you can have various data tables where your actual node data is spread, and you have one table where the references are stored, so you can really have a tree that's made up of, like with files and directory, it's basically the same. A file is one node type, and a directory is another node type. So that's also heterogeneous if you look at it that way. Okay, so what can we do to store trees? The really classic approach is to have a child node, and inside that child node have a field that points to its parent node, which you usually do by storing the primary key or the ID of the parent node in the child. So this is what you classically do with all the n-type trees, unless you have a very small n, then you can use another approach. But the thing is that each child knows its parent, which the other way around means that a parent doesn't know its children. It has to select from the database to get to its children. This way, when you stand on the child, you directly know the parent without any lookups. So this will give you the advantage of having virtually unlimited number of child nodes for every parent node that you have. But you can also go exactly the other way around, which is actually what you usually do with binary trees, because you know you can only have two children. You can just as well take two fields in the parent record and store the links down. So the links are just the other way around. Which means, again, that the parent knows its children, but the children don't directly know their parent. But you can also mix those two. So here you have obviously a limited number of children, because you need one field for each link to a child. But as I said, they're very good for binary trees. And you can also do this, which is kind of a mixture. You just store the relations of the nodes in a separate table from the entire data. So you can basically do whatever you want in any direction of pointers. You just have little relation records that say this ID is child of this ID, or this ID is parent of this ID. And this is actually the most flexible way of storing trees. But of course, if you need to retrieve the tree data back to the client, you need a join for every single select that you make, because you always have two or more tables involved. The big advantage is that this really allows for a simple way of heterogeneous trees, because only in the relation table is where you define where the data really comes from. And this is one killer argument for me, you actually separate the structure of the tree from the content of the tree. You don't have the structure of the tree inside the table where your tree data lies, but you have it somewhere else, which makes it pretty easy to have the same data participate in several trees at the same time, which is pretty hard when you have the fields right in the records. And there's one completely different approach. That's where you basically store, I call it hints for traversal in the nodes. We'll see this later. This is really what nested sets do. And they don't use any primary keys or IDs. Actually, you don't have any direct link between parent and child nodes. Okay, retrieving trees from a DB. Basically, two approaches. First one is something that we all did at some point. That's classical client-side recursion, which means you start, if we take a classical tree walk, you start by selecting the parent node from the database, look at its ID, and then you go with another select and select all its children back to the server. Server gives you back all the children, and on the client side, you loop through all children, and for every child node that you find, you do another select, selecting its children. And so you do the recursion really on the client side. And so this can go as many levels down as your tree is high. Then we have server-side recursion, which is what I'll be basically talking about here. This can be done with recursive store procedures and with recursive CDEs. That's where I have both of them in the presentation here. And then we have one thing that I called neither-side recursion, which is again nested sets, because they are not recursive really. Okay, let's look at some pros and cons. I'll do this with every type of dealing with tree data. I'll have some slides with the pros and cons on it. This is the slide about the pros of client-side recursion, and it's rather short. One big advantage is that the client has full control over the recursion process, because you get every step in the traversal back to the client and can decide there what to do next. So you can really decide what and how you traverse, and you can decide when to stop. If anybody has any other pros of client-side recursion, hands up. I don't know of any. That was it. So now let's see why we don't want client-side recursion. 2 arguments. Slow, expensive. Simple as that. What we really want to do when we want to write efficient programs that retrieve tree-like data, we want as little round trips as possible over the network. So this thing like, I'll pick the parent, back to the client, I'll look at the parent, do another select, go back. It's all round trips across the network that we want to avoid as we can. Next thing is we want to minimize prepare times on the server side, because Holger just mentioned it in his session, prepares are always, sometimes it's the most expensive when it comes to time part of executing an SQL statement. So we want as little prepares as possible. You can minimize those with client-side recursion too by just reusing the data sets. But if you use parameterized queries, this will work. But if you just construct every single select, then you have a lot of prepares doing the recursion, and this is no good. What we really want to do, because we're lazy programmers, we don't want to care about the recursive stuff on our client side. We just want the result set in a recursive way, as fast as possible, and as flat as possible, and if it's somehow possible, just in one go. So this means, again, separation. The server cares about the structure of the tree, and we just care about the content we get back. So, let's start off with first part, recursive store procedures. One thing that's really strong about store procs, obviously, is that they can call other store procedures, and that includes themselves. You can have 2 flavors of that. One is what I call direct recursion. This means that you have one procedure that directly calls itself. And the other one is a bit with a step between, because you can write a procedure A that calls a procedure B, and in there make a recursive call to procedure A. Or you can do this with 3 procedures or whatever you want. So what does a basic recursive store proc look like? Obviously, the recipe basically is the same. You first select the parent node's data, and then you do a select that will get you all the child node's data. And I'm talking about these classic trees where you have the parent link stored in the child. And so for each child, you, inside the store procedure, call the same store procedure, but give the current child ID as a parent. I just saw that some of you have done already recursive store procedures, but I just wanted to show you one example in practice anyway. This is a classic recursive store procedure to retrieve a file system. So imagine we have a file system table. Actually, we don't have to imagine it because I happen to have one ready here. So that's my file sys table. So it's obviously every entity has an ID and has its parent link, the ID of its master record or the directory where it's in. Then I just have a flag indicating whether it's a directory. You don't really need this. And obviously a file name, and then some more stuff that we don't really need. So this would look like this. I've got my root node, where the ID of the master is 0, or null, matter of definition. And then I have my drives. Oops. So the drives again have their IDs, and the directories on that drive link here. The 3 here links to the 3 there, and the 4 here links to the 4 there. So it's a classical child to parent tree. Now, if you want to traverse this, oops, we first select the root node, and then in a for select loop, go through all the children and get their data. So let's see what this looks like in practice. Actually, I've got another tool, which is my own SQL tool, which I use a lot. And there I have those selects ready. Oh, there's the stored procedures. And I don't have the select. Oh, damn, I have to type it. So we'll just have a select everything from SP pulses. It's called dump. Okay. And as an input parameter, obviously it needs the ID of the root node, which is 1 in my example. And it needs a start path, which is just an empty string. And so we'll give back the results kind of flat, but you can imagine this is actually my a little excerpt from my MP3 library. So I have one main directory called mp3lib, and there's a subdirectory for A through Z where all the artists' directories are. And you've got another level with the first letter of the artist. I got a pretty huge amount of MP3, so I have to organize them this way, otherwise I just lose track. And then you have the directory for the artist. Below it is the directory of an album, and below that is 2 entries with actual MP3 files. So this is already 6 or 7 levels deep. Go back to there. Okay, so this is the exact source code. It will just work like that. Another example is bottom-up recursion. So we're doing the same thing, but we stand on a file and we want to know the entire file name. It's a bit different. You select the file name that you're on, and from then on, you recurse up until, and this is the anchor condition, until you hit the master root node of the tree, and just append all the part file names. So this will look like, what was the name? Oh, full path. Okay. Now I need to pick the ID of the node that I want to have the path from. That would be, let's take this one, 14. I think that should be it. Okay. So it really starts with this last part and just recurses up all the way so you get the full path. No big deal. But this is actually something a bit stupid to do, because if you look at this store procedure, this will do exactly the same, just with a while loop. And so you don't have any recursion call, so obviously this will be much faster. Okay. So actually this is all I'm going to show about recursive store process. Yes?
There's one question. You use an execute procedure which returning, is that when you do that in order to report select?
You mean with this example?
Yes, in this example. In the middle where you do the execute procedure.
Yeah. Out of habit. No real reason behind it. It's just, actually this is a pretty old example, and you could do it more elegantly now, but basically what happens is that I wanted to show that really you execute the store procedure. The for select suggests that it's a loop, but it really is an execution, a recursive call. So this shows it a bit better. So pros of recursive SPs are obviously you have the recursion on the server side, so you have pretty few round trips. You just give one select from store procedure and you get all the result data back. They're pretty fast because they are pre-compiled to BLR when you issue the create or alter procedure statement. I always thought that the execution plans for the queries inside the store procs were also pre-compiled at BLR time, but I think this is not really true. But I think the compiler can actually choose a different execution plan depending on the index statistics. Okay. So it gets actually calculated once, but it's not really compiled into the BLR. Okay. Okay. So, but anyway, they're pretty fast, as you know, store procedures are. And they're rather flexible, and then they can handle all sorts of trees in all sorts of ways, just because you can call other store procedures that do sub-recursions or whatever you want. So they can get pretty complex, but that makes them rather flexible. And one thing you should not underestimate, this is the only way I'm going to show you here about managing recursive data, where you have full access to all PSQL features. So you can do inserts, updates, deletes inside store procedures, while the other two ways I'm going to show you are just basically for retrieval, because they're only about selects. But they also have some cons, some negative aspects about them. One is that they're rather inflexible because they are part of the metadata of your database. So if you need flexible ways of dealing with trees, you can either start writing store procedures or even generating recursive store procedures and compiling them into your database. But I'm a bit old-fashioned thinking about this. In my eyes, metadata is something that should be treated as set in concrete. Once we have a database deployed, the metadata shouldn't change on a regular basis. So if you have a simple problem and you have one store procedure that will take care of it, no problem. But if you want to be more flexible and you would have to recompile or reinvent new recursive store procedures, they're not that flexible for that. One thing, if you look from the client side, this is not really an argument when you're the application programmer and the database designer at the same time, which some of you are, I guess. But especially in larger companies, you have projects where you have one guy that programs the application and another one takes care of the database. And for the client, the store procedure is what I call it a black box set in concrete. You can't look into it, and you have no control what happens inside. You can just execute it and take what you get back. That's it. And one aspect is it's got a little better in recent Firebird versions, but especially in the older versions, it was pretty pain. Especially if you have two store procedures calling each other and you need to introduce new parameters, because you always have to drop the store procedures in a certain order or give them empty bodies before you can recompile them. So they can be a bit hard to maintain. And obviously, you need grants on the client side. You need to grant the client the execution right on each store procedure that you make. The other ways we're going to see, of course, also need grants, but they only need grants to the tables where the data comes from. They don't need grants to any database objects other than that. So let's come to the next part, which is nested sets. I can start up. I have a few slides here so I can walk around a little. This is obviously a slightly oversimplified view of the world. And yes, I know it's North America, it's not America, but it was too long to fit in that box, so excuse me. This is just a plain old simple tree like we know it. And if we look at that same data as a nested set, it will look like this. So if you see how the nodes relate to each other, this is exactly the same. It's just another way of drawing it. But the left side is tree theory, and the right side is set theory. That's where nested sets really come from. So, as you can see here, pretty obviously, they're all about containment. So if you have containing structures, nested sets can be very good. So let's just look at some different views of how to look at this data. This is just a 90 degrees tilted version of our classical tree, where I made the nodes so big that you can see which nodes are contained in the other nodes. And we already saw that. So you can see here the borders are somewhat aligned, to give you the idea. And now what you need to think about when you're dealing with nested sets is you need to think border crossings. What do I mean with this? Look at this diagram. Basically the same, just I drew a line right across it. And whenever we cross a border from one element of the nested set into another, we just increase a generator or a sequence and give it a number. So we just number all those border crossings. So when you come into Canada, that's the third. When you leave Canada, it's the fourth. You enter USA, it's the fifth, and so on. So, just a slight variation of that same diagram, maybe shows it a little bit better. So we just have consecutive numbers that end up in two numbers for every node. You see Earth has the 1 here and the 10 there, and USA the 5 and 6. So every node has two numbers that indicate when in the recursive traversal process you enter and you leave the node. So, if we draw this a little bit differently, then we get this picture, which just shows the nodes with their respective enter and leave numbers, which are called left and right values in nested sets. So every node has a left and a right value. And with this given information, you can traverse the tree, because from each point where you stand, you know where to go next. And that's what I mentioned a couple of slides earlier. There's no IDs or primary keys involved here. Those are just numbers. They don't have any other thing to do with the node. This gives some partly very interesting rules for those L and R values. The L value of the root node is usually 1. It's just a matter of definition, but it makes it easier to always start with 1. The L value of every node is also always smaller than the right value, because we traverse the tree from left to right. So lefts always have smaller numbers than rights. Also, the L value of each parent node is smaller than the left value of all its children, because you hit the parent node first, so all the childs have bigger left numbers. Other way around, the R value of each parent node is bigger than the R value of its children, because you traverse the children first and then go back up to the parent. So the parent on the way back will always have a bigger right value. And there's one special thing, just by the fact of the order of traversal, is that the child nodes have an L value that's always exactly the R value minus 1. Because you see, here like Canada, it has 3 and 4. If there was a node beneath Canada, it would need more numbers, so the right and left values of Canada would be away from each other. And actually, this gives a nice trick how you can calculate the child node number of every node in that tree. You see here Earth has 1 and 10. 10 minus 1 is 9. Then you have another minus 1. That gives you 8. And you just divide that by 2, which is 4. So this means that Earth has 4 nodes beneath it. Cool thing that you can do with normal trees. Okay, how can you store those in a database? That's easy. We just need a field for L and a field for R. And in my example, I made a computed field, which is just computed by this formula by R and L. So in every node, you can directly see how many children it has. Now, if you want to insert new nodes in such a nested set, obviously you need a couple of new numbers. So this will look like that. We're introducing Germany below Europe. Europe used to have the 10. Oh, sorry, the 9 here. But now we need the 9 for Germany, so the 9 goes there. It's a child, so its right value is 10. And we go up and replace the 9 with an 11. And now Earth gets the 12. So this division still counts. On the other hand, if we want to delete nodes in nested sets, we also have to renumber. So imagine that Canada at one point in time in history gets assimilated by USA, which is not so unlikely, I'm afraid. We'll have Earth looking like this. So we have to get rid of the Canada node, so we can reuse the 3 and 4 that Canada used to have, just shift them over to USA. But you also see that we have to renumber all the rest. And this is one really bad downside about nested sets. But you can come around this by using combinations. We'll see that. So one last thing here to show is that you can actually move nodes in nested sets. When you have normal parent-child linked trees, where every child has an ID to its parent, all the childs don't have any predefined order. You just order them by whatever you want, but they don't have a predefined order. In nested sets, they do, because if you move the nodes, then you just switch the numbering. So you can see this order of traversal changes. If you're looking from Japan, you say, America is right of me and Europe is left, so I want it that way. Then you have to renumber almost the entire tree, except for the nodes above. They just stay as they are. Okay, actually, I just wanted to show you how you can do this in a database. And I've made quite some examples about nested sets. Actually, all the operations that you can do with nested sets I've put down in stored procedures here. And I hope Holger will make the session material available online someday. Yeah, it usually takes him quite a while from experience. But anyway, there's other stored procedures with full source code is in there. And some of them are rather good documented. Not all of them, but... Okay, so let's just look at this one for an example. This is what you do when you insert a new child node. Actually, I might find one that's a little bit better documented. I think the deletion was... Oh yeah, okay. Let's take this one. Looks better. So if you delete one node, first you get the L and R values of the node that you want to delete. And then you just get rid of the node. You just delete it. So first thing you have to do then is, if this node had any child nodes, you'll have to decrement their L and R values by 1. And this is already a combined tree where I also have a tree level in every node. Because as I said, nested sets alone are pretty awful to deal with, but combined with normal trees, they can be very effective. And the last thing we do is, because this is a combined tree, I also have to update the reference to the parent node, because I also store the parent link in every node. And then there's some more operations you have to do. You have to set the L values to -2 for every node that's farther to the right than the node that you deleted. And then you need a second update for the R values. And so this, I think, is a good moment to switch back to the pros and cons slide, because this shows it quite drastically. Pros is nested sets are really good for static type trees, for trees that don't change much, where you just pump in a lot of data once and you don't go editing around it all the time. So like a catalog for an online shop system, for instance, that doesn't change all too much. Sometimes you get new articles, but once you have it, it usually stays the same. The absolute feature of nested sets is that they are absolutely unbeatable in speed. There is no faster way to retrieve recursive data than nested sets, because the retrieval is non-recursive. You just do a plain select, order by the L value, and you get the entire tree dumped with one statement. And that's what I did in my examples. They can also be mixed with classic trees. So we've seen some of the cons on the slides already. Whenever you change data in those trees, every update, every change is pretty expensive. If you have bad luck and you want to delete the leftmost node in the tree, you have to update all the other nodes in the tree just to get those nested sets ordering back right. So changing is pretty expensive. And we also saw that you don't have any direct links between either parent to child or the other way around. It's just this numbering scheme that gives you a way of traversing the tree, but you don't have any direct links. And one thing I couldn't really make up whether it's a pro or con, because it depends on what you do with your data, is that you have this predefined order of child nodes. If your tree by nature has a predefined order of child nodes, this is good. Otherwise, it may be bad. It depends. So let's...
One little question.
Yes?
Suppose you try to add Asia and say Russia. So that would be possible over there.
Of course it's possible.
But Russia is part of all Europe, maybe.
Oh, I see what you mean. Yeah. No, actually, that's But this also isn't possible in normal parent-child trees. You would need 2 nodes for that. The only way to make this work is with the slide. Well, let me just jump back where we have that. 14. Oh, wrong application error. Yeah, if you do this, that would be one way, because then you can have one node appear in the tree, in the same tree, at multiple places. So that's the only way I know to do it. So let's get back where have we been? 33. Okay. Just some more examples on that. No, change. I just get rid of all this stuff. We have this world table here, which is exactly the example from the presentation. But I've made another table which has a bit more data, so you can see better what it looks like. Same concept. You have planets, continents, countries, regions, and here we have the special. We're in a city that is a federal state at the same time. It's a special in Germany. We have with Bremen and Hamburg. So we're in the Hansestadt Bremen, which is part of the federal state of Bremen, which is part of northern Germany as a region, and so you can see this gives a nice tree structure. And all the nodes have their left and right values. But actually, what I started off with is this. So I gave every node a master ID, a classic link to its parent node, which makes it much easier to, especially when you feed in those data by hand, not using any application like I did. It's much easier to look like, okay, this is North Germany, it has 13, so I want this node, and it should reference this, so I just give it this number. Now the trick is to write one simple store procedure. Let me start off with this one. That's just a classic top-down recursion. It's just the same as what we saw with the file system table, but for this table, which will work something like this, and it will dump recursively all the nodes in the tree. And then I just modified this store procedure a little bit until I got, I think it's this one, version 3, which, while traversing the tree, has 2 counters, an in counter and an out counter, which will give the left and right values. So what I basically do is I go through this tree once, and while traversing it, I just fill in all the L and R values. It's a rather simple algorithm. You can see it's not very long. And it's a DML procedure, so you have to select all the output because you have to traverse the entire tree once to go completely through it and cross every node. And here's, again, classic top-down recursion. I execute the same procedure with my current child ID that I'm on, with the out counter, and I get back the new out counter. And you can take a look at this if you get the examples. And on my way up, I just fill in all the R values on unwinding the recursion. So that makes it rather simple to use this nested set because you feed it just like a normal tree, and then you just run this store procedure once, and you get your nested set back in place. Actually, once I had this, I said like, why was I so stupid to write all these complicated nested sets, update, insert, delete store procedures? Just do this in the classical tree view and run this store procedure again, you're done. It's much faster, actually. But it should be just an example on how you can treat those nested sets, so I guess it's all right. So once we have run this store procedure, we can do some good old plain selects on it. Okay. So this would be the first example. Now you see that if you do a normal select, then you get all the nodes in the right order, but you don't see on which level they are, which doesn't give a nice visual representation of the tree. So a simple trick is in every node you store the tree level the node is on, and then you can use something like this. You just take the left part of a string of certain length, and the parameter for the length is the tree level. And then you just concatenate the actual name you get. And so when you execute this, you get this nice looking tree structure. And as I said, this is really the absolute killer feature for me for nested sets, is you just do a plain select, order by an indexed field, an integer field, which is about the fastest index you can have, and you get a completely recursively traversed tree structure back without any recursion. Okay, let's see if I have some more examples here. Oh yeah, here's the same example, but with the child count, which is just calculated in the select by using this formula for the childs, so you can directly see how many child nodes every node has. And you can also do path retrieval, so you can do a bottom-up recursion with nested sets as well. It just looks a little bit differently. Basically, you just join the node that you want to have on the parent node, and the result set gets ordered by the L value of the nodes. And then you get this. So you start off with Earth, go down to Europe, and then to Germany. So it's the other way around, but you can just switch the order. And so you get to where a node lies, to the path of the node. I have some more examples here. Let's look at this one, for instance. This one will give you only the leaf nodes. So if you don't need the nodes that have child nodes, but just the childs, then that's simple, because you can use this formula as a work condition. So just give me back all the nodes where the R value is bigger by exactly 1 than the L value. And if you execute that, you only get the leaf nodes, but there's no Europe and no Germany here because they have many or more than 1 leaf nodes. Okay, I think this was the last slide, right? And we're just about in time, actually. We have a couple of minutes. So I don't want to start with recursive CDs. We'll do this in the next hour. Do we have questions so far on this part? Any questions? None? No questions? Oh, okay. Okay, that should be enough then. Then I would say let's have a quick break of half an hour, and then we'll go on with the really cool recursive common table expressions. See you in half an hour.